Welcome to my talk on finding new diamonds. Suppose a new promising medication needs to be investigated. Before it can enter the market, it has to pass a number of tests. At some point, it will need to be tested on humans in a clinical study. Before the study can begin, a sufficient number of eligible patients has to be found. Depending on the study, they have to satisfy very specific criteria. For example, a criterion might ask for patients that suffer from a form of cancer that is not skin cancer and should not have been treated with a certain medication in the past 6 months. On the other hand, every time a person visits a doctor or is admitted into a hospital, new notes will be added to the person's electronic health record. Unfortunately, the records are very unstructured and contain many medical abbreviations. So even for medical experts, it is very time-consuming to assess if a patient can enter a study or not. We aim to build a system that can support experts in finding eligible patients. The system should represent the medical background knowledge and the electronic health records in a structured way using description logics. First, the medical concepts have to be extracted from electronic health records and then put into a temporal ABox containing sparse temporal facts. To give our system some background knowledge, a biomedical ontology like SNOMED can be incorporated into the T-box. Once the knowledge base is defined, the criteria of a given clinical trial need to be translated into a formal query language. We propose to use metric temporal conjunctive queries with negation as the query language, since it supports temporal operators and negation. This is needed to express, for example, that a patient should not have been pregnant in the last year. In this talk, we will focus on how to temporalize the description logic EL, and then how to answer temporal queries over this logic. In order to represent temporal information about diseases and other findings, we employ certain diamond operators. Suppose a fact P holds at the time points denoted in blue. The negative diamond operator, also known as since, holds then at all future time points after P was true for the first time, denoted here in green. The positive diamond operator, also known as eventually, holds at all time points before P. The next diamond operator is not a standard operator. We call it the convex diamond. Suppose a patient broke his leg 2 weeks ago and he got to wear a cast. If a patient is still wearing a cast 2 weeks later, it is reasonable to assume that he was wearing the cast actually in between two. The convex operator is true everywhere in between 2 time points where P is true, so yeah, basically fills all the gaps. Now suppose the patient with the cast is still wearing a cast after 10 months. In that case, it would be unreasonable to assume that he was wearing a cast in all the meantime, because the time points are simply too far apart. In cases like this, the bounded convex operator is more useful. It is true everywhere in between 2 time points where P holds, but only if they are at most 10 months apart in this case. The diamond operators can also be seen as closure operators on sets of time points. For example, if we apply the convexity operator to the set of time points at which P holds, it returns the set of all intermediate time points between the earliest and latest time point in the input set. When we view the diamonds in this way, it can be shown that the set of all diamond operators is closed under pointwise intersection, union, and composition. This property will prove useful when we look at the completion of the T-box. In our temporal description logic, we allow the use of the diamond operators on the left-hand side of GCIs only. For example, we can express that if somebody has been diagnosed with diabetes at some time point in the past, then he is also diagnosed with diabetes at the current time point. As mentioned before, we can use the bounded convex diamond to express things like if someone was diagnosed with a broken leg at 2 time points at most 8 days apart, then his leg was also broken in between the 2 time points. The logic TELH bottom with convex diamonds and operators only on the left-hand side basically extends ELH bottom by allowing arbitrary temporal concepts and roles on the left-hand side of GCIs. However, we can limit ourselves to the following normal form, which is able to simulate any temporal concept on the left-hand side. Here the diamond star is just a placeholder for any of the available diamond operators. For those not so familiar with the syntax of description logics, each temporal GCI can be seen as a two-sorted first-order formula with up to 2 object variables and 1 temporal variable. So in this logic, we could show that that entailment is p-complete by extending the completion procedure from ELH bottom. So, for example, the first rule says if there is a temporal chain in the T-box where A1 implies A2 and A2 implies A3 with 2 different diamonds in front of it, then A1 also implies A3 with the composition of the 2 diamonds in front of A1. Similarly, if A implies A1 and A implies A2 with respective different diamonds in front of it, and the conjunction of A1 and A2 implies B, then A also implies B, this time with the intersection of the 2 diamonds. As mentioned before, the diamonds are closed under intersection, union, and composition. And additionally, if bounded convex diamonds are combined with any other diamonds, then the result is never a new bounded convex diamond. So this guarantees us that during the completion, only a finite number of additional axioms will be added to the knowledge base. The ABox completion rules can also be extended in a straightforward way. Suppose diamond A implies B. We then view the diamond as a closure operator and input the set of all time points at which small a is part or it belongs to the concept big A, to obtain the completed set of time points at which a diamond of big A of small a holds. For each such time points, we know that B of A also has to hold, which is why we add it to the ABox. So there's one special thing about time points in our logic. Because information about a patient usually contains large temporal gaps, we assume that only the time points are defined at which some facts exist. So in order not to introduce exponentially many intermediate time points, we limit ourselves to one representative for each intermediate interval, which leads to a linear number with respect to the input of time points in the ABox. So here you can see, suppose just the blue time points occur in the ABox. So then for each interval, we introduce only one representative time point that captures the behavior of every time point in that interval. By the choice of our diamond operators, the behavior in these intermediate intervals is always constant. So when we want to know whether a fact is entailed in an intermediate interval, we just have to check if it holds at the representative time point for that interval. So that was the underlying temporal logic. Now looking back at the big picture, what is missing now is the formal query language, which we are going to look at now. So metric temporal conjunctive queries with negation. Consider the following criterion. Diagnosis of rheumatoid arthritis of more than 6 months and less than 15 years, which is taken from an actual clinical trial. To represent it in a structured query language, we choose empty NCQs. So, for example, the criterion corresponds to the following query, where we use metric box operators that can be read as always in the last 6 months up to now, for the first one, for example. So the whole query can be read as there always has to be a diagnosis of rheumatoid arthritis during the last 6 months, and there should not always have been a diagnosis of rheumatoid arthritis during the last 15 years. In empty NCQs, the atoms consist of conjunctive queries with atomic negation, and these atoms can then be combined by arbitrary metric temporal operators and negation. So this leads us to the next problem. Usually it is stated that a patient is diagnosed with something, but not what he is not diagnosed with. So negative information is rarely entailed and also not present in our logic. To get reasonable answers, we use the idea of negation by failure. And the semantics we use are called minimal world semantics. Suppose the following knowledge base about diabetes patients. A diabetes patient is someone diagnosed with diabetes, similar for diabetes type 1. Diabetes type 1 is a special form of diabetes, and there is a patient P that is a diabetes type 1 patient. For this patient, we can construct a canonical model in which he has two diagnoses, one with diabetes type 1 and one with just diabetes. This model is universal, which means that it is homomorphically contained in any model of the knowledge base. This can be exploited, for example, when answering conjunctive queries without negation, since all answers over a universal model are certain answers. However, when negation is allowed in the query, it suddenly makes a difference whether the second diagnosis is there in the model or not. Currently, the patient has a diagnosis with diabetes that is not diabetes type 1. However, if a patient is mentioned to be just a diabetes type 1 patient, we would assume that he has just one diagnosis of exactly diabetes type 1. Therefore, we require the canonical model to also be minimal. It has to contain the least number of individuals to still be a universal model. In this case, it means that D2 is redundant and we can omit it to obtain a minimal model. To those familiar with cores of graph structures, in the case of ELH bottom, the definition of minimality actually overlaps with the notion of a model that also has to be a core. In minimal world semantics, just the minimal canonical model is used to answer queries. Therefore, it enables a form of negation by failure. If a diagnosis is not required to be there, we assume that it's just not there. Since we want to answer temporal queries, we need to temporalize minimal world semantics. Here we have the two temporal diabetes axioms from before, expressing that both diabetes and diabetes type 1 cannot be cured so far. Intuitively, a temporal minimal canonical model can be constructed by completing all the facts about named individuals at each time point and then computing the minimal canonical model for each time point separately. For this to be so simple, we have to make a restriction. So far we could not find a way to make temporal roles work with minimal models, which is why we do not allow them here. Without temporal roles, all temporal interactions are effectively limited to the named individuals. We can express that the patient is suffering from diabetes at all preceding time points, but we cannot enforce the same anonymous diabetes object. Each time point will introduce its own diabetes object. If it is really necessary that they are actually sharing the same diagnosis object at all time points, then the object would have to be explicitly declared in the ABox. The temporal minimal model is infinite in both the object and the temporal dimension, which is why in order to answer empty NCQs over the temporal minimal model, we employ a combined rewriting approach. In this approach, the canonical model is compressed to a finite structure IA fin, and the query phi is extended to a first-order query phi of t, which gives the correct answers over the finite interpretation I fin A. I fin A, yeah. So the rewriting consists of two steps. First, we reduce a non-temporal rewriting of conjunctive queries with negation over ELH bottom knowledge bases, which essentially allows us to use only a finite object domain. We then use the fact that intermediate temporal intervals stay constant. This allows us to represent the temporal dimension in a finite way. To interpret this finite structure accordingly, the query needs to be rewritten so that it takes into account this different structure. The rewriting is quite technical, so if you are interested in details, I recommend you read the full article. Through the rewriting, we can finally show that in our temporal version of EL, entailment of rooted empty NCQs is X place complete and P complete in data complexity. This is a promising result, in our opinion, since while the queries are quite small, the provided medical data can get quite large. And due to the lack of time, I would like to stop here and thank you for your attention.